featuring Cambridge University's Dr. Chris Smith. This is Ask the Naked Scientists.
You are with Cape Talk.
Views and news with Clarence Ford.
Welcome, Dr. Chris Smith. Always good to have you on a Friday.
Happy New Year, I think is also
Indeed.
the order of the day, isn't it? Yes, it's our first show in 2024. Can't believe we're saying that. Where did the last year go?
Exactly, and I forgot it's New Year. There's only 360 days left to the next year.
Oh, no.
And it's flying by. In no time, we'll be wishing each other again. Well, hopefully I still have my job by then. Welcome. Maybe we should just go straight into the questions. And this one reads from Solly. Dr. Smith, I know you can determine a tree's age by counting the rings, but that means having to cut down the tree. Is there not another way of knowing this without killing the tree?
Yes, what's being referred to as dendrochronology. Dendro as in dendrites, branching trees, chronology as in time. And the way tree rings work, most people are familiar that trees grow seasonally, and every year of growth is an additional tree ring because of the laying down of new material that tends to peak during the growing season and then retreats to a minimum in the quiescent time when the tree is dormant, mainly over winter. So if you count up those rings, you can see how many seasons the tree has grown through, and also the thickness of the rings tell you what the conditions for growth were like. So not only do you get a time profile if you look at those rings, you get a season profile as well, and that's how we know weather patterns going back hundreds of years, because we can look at old trees. But exactly as is being suggested, you got to cut it down to have a look. There are other ways to do this, though. You don't have to cut the whole tree down. You can take a sample, a core, across the tree, and this gives you access to that ring pattern and to some of the material inside the tree, which is inside the trunk, without having to cut the whole thing down. But anything that does damage to a tree is potentially going to jeopardize it. But that's one way of doing it. You can take a sample as a core rather than having to take the whole trunk and count the rings manually.
Okay, there we go. Solly, your question answered. Janus in Fishhoek, welcome. Happy New Year, and go ahead with your question.
Good morning to both of you. Good morning, Dr. Chris or Professor Chris, or this your title. My question is regarding the water on the Earth. We know that we've got the water coming from the rivers, from the mountains, and going down to the oceans. But when the water from that inside is pushing through the pressure to the top, but the water inside, where does water came from?
Right. So the question concerns the origins of water on Earth, one of the most abundant molecules that we have. And the answer is that when the planet first formed, we used to think that it was very, very dry. It was just gas and dust, and then the water came later. We've got evidence, in fact, there is quite a lot of water probably mixed in with the material that made the early Earth, but it's still added to later on during Earth's history by the arrival of, to an extent, comets, but to a greater extent, asteroids. How do we know this? This is because we can look at the isotope fingerprint, because different molecules and chemicals come with slightly different masses. There are different forms or flavours of the same element called isotopes. This is because they have extra numbers of neutrons in the centres of some atoms, and different atom isotope types tend to be found in certain environments. So if we look at the fingerprint of water we've got on Earth, and then we look at the fingerprints of the water we've got in things like comets and things like asteroids, you can ask what proportion of the water that we've got here today probably came from each of those sources. And so our current view is that there was some water mixed in with the material that made the Earth about 4.5 billion years ago, and it was supplemented probably in the first X number of millions to hundreds of millions of years of the planet's history, to maybe its first billion years or so, by the arrival of lots of comets and other impactors that crashed into the Earth from outer space as the solar system was configuring to take up the situation that you see today. So it's a mixture, is the answer.
Interesting question in about the Three Gorge Dam in China slowing down the rotation of the Earth and making the day longer. Is there any truth to that?
The mass of the Earth is 6 followed by about 24 zeros worth of kilograms, or 6 followed by 21 zeros tons. So a massive, massive thing. And if you think about how much a dam weighs and how much the water behind the dam weighs, it's not not inconsequential. It's a significant mass, but it's not enough to make a massive difference that we would measure. You could measure it if you had extremely precise materials and devices, and in fact we can weigh bits of the Earth from space, and I'm using the word weigh loosely, but that is not going to make a massive difference to the Earth in a demonstrable way that will have an impact that we will really experience at a human scale. But the experiment I'm referring to in terms of weighing the mass of the Earth, there are projects, including one called GRACE, which is a pair of satellites which are in orbit around the planet. And because they are a couple, one satellite is watching the position of the other satellite by bouncing a light beam from one to the other and timing how long it takes. As those satellites go over the Earth's surface, one is slightly ahead of the other, and therefore if a patch of the Earth's surface has more mass than another patch, the satellite in the front will be accelerated due to gravity slightly faster and slightly ahead of the one coming along behind. This will stretch the light beam between the two very slightly, so you can see how the acceleration has changed, and therefore you can see how the gravitational effect of that patch of the Earth's surface has changed, which is directly proportional to mass. And this is one way in which researchers are working out how we redistribute water around the Earth because of global warming. As we lose ice from structures and bits of the Earth's surface, like Greenland, for example, we can see that reflected in a loss of mass from that patch of the Earth's surface, and that in turn affects the gravitational field over that patch of the Earth, and we can measure that. So you can measure these things. They are discernible, but will they make a discernible and a human context impact on day length and so on? No, that's not going to have any kind of impact that I'm going to get up tomorrow and notice.
Okay, that sorts that out. Now, Zuki in Big Bay is on the line. You have a question probably related to our summer at present. Welcome, Zuki.
Hi, Clarence. Hi, Dr. Chris. So yes, I've got a question about the UV index. How is it determined? What are the factors that determine how strong it is or how weak it is? And also, how does UV rays coming off reflective surfaces like white sand or white water, how does that affect the strength of the UV radiation that reaches our skin?
Ultraviolet, or UV, is one component of the spectrum of radiation that comes from the sun. When we look at light coming from the sun, it looks white, but it's actually a whole mixture of different wavelengths or colours of light. And at one end of the spectrum that we can see at least is red light, and at the other end of the spectrum that we can see is bluey purple light. But if you carry on going to smaller and smaller, more energetic waves, you get into the UV. So the sun is a source of lots of different electromagnetic radiations or light waves, and UV is one part of that. And UV isn't just one thing. There are very, very short, powerful UV rays called UVC. There's some slightly longer waves called UVB, and some longer than that waves called UVA. So all of this arrives out in space and bathes the Earth. But it's got to come through the atmosphere. And the Earth's atmosphere is quite good at soaking up and attenuating UVC, so that doesn't arrive. UVB does get through a bit, and UVA gets through a bit more. We do, though, have at about 15 kilometres up an ozone layer. And this is molecules of ozone, 3 oxygen atoms glued together. And the structure and shape of that molecule and the bonds between the oxygen atoms are perfect for absorbing ultraviolet rays. So as the UV comes through, a lot of it gets soaked up by that ozone layer. And in fact, it's thanks to that we are here at all. Because if we were allowing all that sizzling UV to come straight down onto the surface of the Earth, because those waves are so energetic and so damaging, they would make life, certainly as we know it, much harder to happen. But because we have that ozone layer, it protects the Earth and protects us by absorbing a huge amount of the particularly shorter wavelength, more damaging ultraviolet, but some still makes it through. So when it then gets to the surface, we know that each square metre of the Earth's surface gets hit by light delivering energy at the rate of about a kilowatt. So when we're measuring a UV index, we know roughly how much energy is arriving over a patch of the ground at any moment in time. We know what proportion of that energy is in the form of UV, and we can make predictions based on what's in the atmosphere, the density of the atmosphere, other things that may attenuate the path of the UV through the atmosphere onto the surface. We can make guesstimations because we have lots of measurements of how this works now, so we can work out when we're going to have a high or a low UV exposure. And then you've got reflective effects. You will get effects if you have a highly reflective surface. If you go skiing, for example, then snow, lots of water crystals, looks white because all the tiny crystals refract or bend all of the wavelengths of light, all the colours, including UV, back at you, making it look white. The UV will therefore bounce back off and hit you. So any white surface is going to potentially be reflecting all the different colours, including the UV, and that's why you can get burned. So yes, there'll be some geographical distinctions about where you are exposed to the light coming in, but we have a sort of standard measure that we use when we say this is what the UV index is. So it's relative, it's not an absolute thing, because it will have an effect of geography built into it or intrinsic to it.
It is our regular interaction with the Naked Scientist, Dr. Chris Smith. Joins us every Friday just after 9:30, an opportunity for you to ask that question that keeps you awake at night. For the next question, I suggest you get your popcorn. I'm doing exactly that. Please ask Dr. Chris what flips inside a human's brain when they enter politics. What turns them into genocidal maniacs? Also corruption. Do their brains change somehow? A question that Dawn asks on behalf of so very many South Africans.
Hi, Dawn. Well, of course, what we don't know is whether it's cause or effect. Are people who have other agendas, have other behaviours intrinsic to them, more likely to be drawn into politics? Or does being drawn into politics alter people's behaviour? Or is it both? We don't know because no one's actually done the trial. But really, what attracts people to a particular job are going to be a range of factors. It's going to be various pull and push factors. There are some people who want to make a difference. They want to make a difference for good, and the way you do that at the scale of whole populations is you go into areas that make the policies that those populations adopt and live by. There are other people who have other more nefarious intents, and they think, well, if I get into a position where I can influence people, then I can influence the kind of people I want to influence and change the game in my favour and load the dice, etc. So really, I don't think there's a straightforward answer to this. I think it's a range of things, and there are people who go into these things with the best intentions and remain with the best intentions. There are people who go into these things with good intentions but then can be seduced by other opportunities and maybe biased by other things that come along and may steer them in another direction. And then there are going to be people who go into these sorts of things with all the wrong intentions, and they're always going to be a bad apple.
Absolutely, maybe too many of those. Let's talk about Fahrenheit versus Celsius. Is Fahrenheit obsolete? Vaughan Kleinschmidt wants to know.
These are just interval ratio scales of measuring how much energy there is in particles. What temperature actually is a measure of how fast atoms are colliding with your thermometer. So when I put my thermometer in a cup of water, for example, and I register a temperature, the atoms are colliding with the thermometer, bashing into it and giving some of their energy to the material inside the thermometer, which makes it have more energy. And if it has more energy, the atoms spend more time apart from each other, therefore they get bigger, and therefore the fluid inside the thermometer expands, and you say, oh, the temperature is higher. You're measuring an average energy of particles in the environment. The minimum energy particles can have is 0 Kelvin, and 0 Kelvin is minus 273 Celsius. And what we call 0 Celsius is already hundreds of Kelvin, and Fahrenheit even more. But they're not the same gap between each degree. 1 degree C, 0 to 1 degree C is not the same gap as 1 to 2 Fahrenheit or whatever. They're slightly different gaps between the two. So they're different ways of measuring the same thing, which is how much energy particles have. But because we tend to adopt the metric system, Celsius has become de rigueur and we all use it, but Fahrenheit is still used in other places and people who haven't embraced that system, and it's still completely meaningful.
Then we have Tyrone on the line. Hello, Tyrone, Kales River, welcome, Happy New Year. Go ahead with your question.
Morning, Carrie. Compliments, Dr. Smith. Morning. Doctor, can a subatomic particle like a neutrino or a quark hit something while passing through Earth and cause a subatomic explosion, an atomic one?
It really is a bad line. I'm hoping you got that one, Dr. Smith.
Not really, but I think it was about neutrinos, and it was about whether or not neutrinos streaming through us can cause subatomic things to go wrong or other explosions and so on. Neutrinos are so named because they are absolutely tiny, and the word neutrino, it's because of the people who discovered it and where they came from. It was called the neutrino because it was a tiny version of something that appeared to be a baby neutron, or it didn't have a charge and it didn't interact with things electrically. These particles are hard to study because they are only weakly or only occasionally interact with things like our detectors. And therefore, if you can't detect something, it makes it much harder to study. We know they exist, we can detect them, but you just need enormous systems to detect them. And there are billions of them streaming through us all the time. If you look at the sun, for example, it's pumping these things out all the time, and they are streaming through us all the time. But most of the time, they go straight through, and we have no knowledge that that's happened. So, no, I don't think it's very likely at all, based on the odds that these sorts of interactions are happening or potentially happening billions of times a second to all of us, that there's any kind of threat, because given how long the planet's been here and given how many of these things are streaming through us all the time, if the odds were high that this was going to happen, that some weird physics was going to go on, then I think it would have happened by now. So no, I'm not concerned.
Gotcha. And again, I'm going to grab my popcorn for this one. Dr. Smith, what happens after death? In a condensed version, thanks, says Anthony. Don't you just kind of rot?
Well, when we die, we don't instantly switch off. When we die, the consciousness is usually expired. In other words, the experience, the perception of the world around us that is ongoing in all of us, that we call consciousness, that stops because the brain cells stop talking to each other in a coherent way that makes us aware of what's going on. But when that happens, we don't instantly die. All of the cells in our body don't suddenly become inviable. It takes time for cells to run out of energy, and for that they need oxygen and sugar, and they don't instantly have no oxygen and sugar. So for a period of time after we die, we're still alive in terms of individual cells are still alive, but slowly they will run out of energy, they will run out of oxygen, and then they will run out of the ability to maintain an electrical gradient across their cell membranes. And we use those electrical gradients in order to keep the cells viable. We pump things we don't want in cells out, and we bring in things we do want using this electrical gradient that we create across our cells. And if that breaks down, the cells then fill up with the things that shouldn't be in there, which makes them swell up and burst, and then they become completely inviable. So there's a period of time when our body is still potentially viable, but it's just not conscious. The systems aren't all working and talking to each other, so it's beginning to shut down and die, but it hasn't completely become inviable. Once you get to the point where those tissues begin to become destroyed by a lack of energy and driven by oxygen deficit and sugar deficit, then you start to break down the cells. They actually burst, smash apart, and start to digest themselves with the enzymes that are locked up inside them. And at the same time, we are full of microorganisms. There are trillions, probably 30, 40 trillion microorganisms in our guts and elsewhere on our body. And they cease to be held in check by our immune army, because the same thing that's causing the rest of the cells in the body to stop working is going to affect the immune system, which was holding back the tide of bacteria. They then begin to grow out of control as the immune army retreats. And then you begin to break down your tissues, not just because they're breaking themselves down, but your defences are down, so you then are invaded by these microbes that go all through the body and start to smash up all the molecules and dismantle you from the inside. And then other microorganisms join the party from the environment and help to break you down. And in this way, you recycle all of the nutrients, all of the things that made you, into the environment, where they're then carted off and used by life elsewhere on the planet for millions of years to come.
There we go. And I think on that particular note, we're gonna wrap up. Big thank you to Dr. Chris Smith, the Naked Scientist. For now, it is nearly time for news coming your way at 10 o'clock exactly.